So we're working this problem that we've drawn a free body diagram for, in which we've been asked to find the acceleration of this 5-kilogram suitcase, which is going to accelerate down a ramp that's inclined at 30 degrees. There is a frictional force opposing this motion of 15 newtons, and we've done the free body diagram and we've labeled it, and we've also written the expressions for the components, the x and y components of the acceleration and FG vectors here. So we're now ready to analyze the motion in the x direction and in the y direction. So we'll go ahead and set up to do that. And let's acknowledge the things that we have that are known. First of all, the friction force was given in the problem is 15 newtons. And then if we use 10 as our value for the magnitude of acceleration due to gravity, 10 meters per second squared, to just make the computations easier, then what we have in the x direction, Fg sine theta, which is 30 degrees, then we have 5 kilograms times 10 meters per second squared, which is 50 newtons, times the sine of the angle, which is 30 degrees. We have 25 newtons in the x direction, and that is the force that's actually going to be causing this to slide down the ramp. It's not an applied force, it's gravitational force, but it's as acting as if as an applied force, because it's what's pulled due to gravity, pulling that down the ramp. Then, just for the heck of it, not that we were asked to find it, but if we're doing the components, we may as well go ahead and do force due to gravity in the y direction, the y component of that, because that's actually the component that is equivalent to the normal force, and the problem might ask us later on for the normal force or something to do with that. But for now, let's just go ahead and do these x and y direction equations. So we can see, let me take this suitcase away here, we can see from our arrows in our free body diagram that the normal force and the y component of Fg are opposite, and they are the same length, which means that there's no acceleration in the y direction. The acceleration in this problem is all in the x direction down the ramp. So we can go ahead and in the y direction, at least, we can write that since there's no acceleration, then that means that the net force must be equal to 0, and that means that the normal force minus Fg in the y direction add up to be 0, which then we can see from that algebraically it means that the normal force, whatever that is equal to Fg in the y direction. And since we've already shown from our little bit of trigonometry there that Fgy is equal to 43.3, the normal force is also equal to 43.3. So 43.3 newtons is equal to 43.3 newtons. Okay, so that's just extra. We weren't asked to do that, but we can do that easily from the free body diagram. What we were asked to do is figure out what's going on in the x direction. So let's let me take a green pen to do the x direction, and let's say that based on the free body diagram, the net force is equal to the mass times the acceleration. So that's restating Newton's second law. And acceleration is going to be happening down the ramp. So what that means is F net is equal to Fg in the x direction, and that's this arrow here, the green arrow pointing down the ramp, subtract frictional force, which is pointing in the opposite direction, and that is equal to the mass times the acceleration. So if I now rewrite this, leaving out the word F net because this is the part of the equation that I'm most interested in, mass times acceleration is equal to Fg in the x direction minus Ff, frictional force, which means that if I'm solving for acceleration, which is what the problem asked, find the acceleration, then I need to isolate the a in this equation, which means I'm going to divide both sides by the mass. So Fgx minus Ff all divided by mass. And let me move this up so we can see it now. And now that I've got this written algebraically solved, I'm going to go ahead and replace variables with values. So acceleration is equal to Fg in the x direction, we said was 25 newtons. So 25 newtons minus the frictional force, which we were told is 15 newtons, all divided by the mass, which we know is 5 kilograms. And newtons divided by kilograms, of course, are going to be units of acceleration, and that is equal to 10 over 5 newtons kilograms, and that's equal to 2 newtons per kilogram, which is also equal to 2 meters per second squared. And there you have it. So therefore, the case will be accelerating down the ramp at a rate of 2 meters per second squared. I said my therefore statement instead of writing it. So therefore, acceleration of 2, and let's just keep it to 1 sig dig here, 2 meters per second squared down ramp.